Hey folks, how you all doing? All right? You enjoying the complimentary food and drinks and everything? It's great to see so many of your faces here. It makes me so happy. I spoke at NDC last year, which you may or may not remember was just all virtual. So I spent an hour just talking to a camera, which, believe me, it's not the best kind of way. You don't get the most sort of feedback from the audience. So having seen so many faces here makes me really, really excited. Now, just a heads up, I might ask you at one point, maybe two, for a little bit of audience participation. Now, this is not dangerous. You feel free to join along. Don't do it if you don't want to. It's all in good fun anyway. Anyway, welcome to this little session on building WebAssembly games with Rust. How we move video games from consoles and on your local machine and into the browser. So let's start with a little sort of outline for what we're going to do today. The duration here is actually about correct. We'll spend about 45 minutes of me just talking, you listening. At any point, if you've got any questions, feel free to just shout out, raise your hand or whatever, and I'll try and answer them as we go along. There's really no strict schedule we have to follow. Anyway, the talk is divided roughly into three parts. One is how do you even get started, and what are the tools that we want to use when building these games. The second is when we put it together, how do you actually build the game? What sort of adjustments you need to make to build a game for the web instead of for a native platform, as we say. And finally, when it's actually working and it builds for the web and it plays, what sort of concerns do you need to have in mind when building for a platform such as the web? How is it different from native and what you need to optimize for? Anyway, let's start with a little introduction. Hey folks, I'm Thomas Heartman. I'm currently a developer community manager, sort of developer relations-ish, very vague. I don't know what I'm doing, my boss doesn't know what I'm doing. It's pretty good. I used to be a full-stack-ish developer. I've been everywhere. I've done a bit of front-end, I've done a bit of back-end. Not an expert at anything, but I'm just really, really curious. I really like playing around and learning new stuff. Now, I'm a Rust enthusiast, or a Rustation, as we like to call ourselves, and I co-host the Rust Oslo meetup group. So when it was time to write a game for the web, it was pretty obvious that, yeah, I'd go for Rust. Now, I don't have a very impressive CV at all. I haven't built massive projects. I don't maintain curl or anything like that. I just like to learn. I'm curious and I like playing with things. And more than that, I love video games. And I have ever since I was a kid. Now, when I was a kid, I was my mother's first child, right? And she was quite conservative. And she didn't really want to let me watch TV for too long or play games or do anything. So I always had to go to my friends' places to play, right? And I was always super excited. But then, lucky stroke, I got really ill. That meant that I had to stay home for weeks. And my mother was sort of scratching her head thinking, well, how am I going to entertain this kid? I got to get some work done as well. Turns out the solution is a Nintendo 64. I was super excited, right? So I spent a couple of weeks much like this kid, yeah? Just playing Super Mario 64 and Banjo-Kazooie and just loving everything. And since then, I've loved games all the while. Sadly, as I'm sure a lot of you can relate to, once you grow up and you start a job, you don't get as much time to play as you want to. But that doesn't mean that my mind doesn't immediately go, games, this is cool, can we do anything with games with this? So that's why I thought, yeah, let's write a game. Oh, by the way, I just realized, you can see my address bar and stuff. I'm really sorry about that, but I haven't found a way to both show full screen the presentation and my speaker notes. So you'll just have to live with it. It's fine. Anyway, yeah, so writing a game for the browser using Rust. There's a lot of moving parts, and it could be really, really difficult. But I had hoped it would be harder, because it's actually not. It's surprisingly easy. And when I found that out, I figured, oh shit, I got to think of something else now to talk about for an hour, right? I got to have something to show. And luckily, I do. So just sit along and enjoy it. First off, why why even write games with the browser, right? Like, why not just deal with native games? Aren't they great? I mean, sure they are, and they're optimized with the various platforms. But that's the thing. They're various platforms. They run on multiple separate instances. That means, like, if you're on a computer, you need to download the right file for your operating system. If you're on a phone, you need to get the right file for that and everything. And I'm sure if you've played games, you can also relate to the fact that, oh, you might not have this DLL installed, or you need to link something, or things just stop working. With the browser, you've got one target. And this target runs on pretty much all modern systems. So it's pretty easy, right? You go, oh, well, you put it here, everyone can get hold of it, they don't need to download anything, it's just there right in the browser. So it's a great way to sort of make things accessible and let people see what you're working on without having to download stuff and spend a lot of time getting set up. That's what makes it really exciting to me. Now, how do we get started with this? As I said, I had a goal. I wanted a game in a browser. That means probably WebAssembly. You could do just JavaScript and play with the canvas and all that stuff, but it's more fun if it's WebAssembly. And second, as I said, I love Rust. Naturally, let's try and put them together. Now, I also specified that this talk does not require any sort of Rust knowledge, so don't worry, we're not going to dive deep into like the internals of how this function works or all that stuff. It's all mostly pretty high level. There's some optimization stuff later that gets a bit into the weeds, but just hang out, I'm sure it'll be fine. Anyway, let's talk about Rust, because, I mean, why would you choose Rust? And Rust's mascot, Ferris, is probably a bit hurt that you would even ask. But for me, it was never really a question. So let's talk about Rust. Rust is a systems programming language, is what they bill it as, but it's basically just a programming language that looks a lot like C. It's got the C-style structure that you're probably familiar with from C#, from JavaScript, and from all of that stuff. Now, this isn't a Learn Rust talk, so this is probably the most we're going to see syntax-wise. So just so you know, it's something you're familiar with. Rust is a compiled language, much like, again, C# and Java. So as opposed to JavaScript and Python that are interpreted, that means you build it once, you get a binary, and you can distribute the binary. You don't need to distribute the source files, right? Next, there's no runtime, and there's no garbage collector. This is more similar to C and C++, where you need to do manual memory allocations to make sure you free and allocate the memory you need. Rust does this slightly differently. It has something called the borrow checker, which means at compile time, when you build everything, like in your source files, you have to declare and make sure that everything works, that the memory is freed and all that stuff, but Rust does it for you. It just makes sure that it doesn't compile unless things work. So this stops you getting memory leaks and stops a whole host of bugs. So it's really, really useful for that. It's also fast and memory efficient. And this goes back to what I was saying in terms of it not having a runtime, not being garbage collected, right? So like C and C++, you get really, really high performance, and you don't have these slowdowns when you need to sort of collect all the garbage or start up the runtime. So you get away from that. Now, what about me? Why do I like Rust? Because, I mean, this is great language-wise, but what is it about the language that draws me to it? I mean, sure, performance is good, it's all well and good, but I don't really encounter that a lot when I just do my own coding in my spare time, right? Why do I need to worry about that? So I think one of my favorite things is Rust's type system, which is really, really expressive and is actually Turing complete. You can build a program with types such that it doesn't compile because it just never finishes, the holding problem, right? In the compilation will stop because of a Stack Overflow error at the end or a recursion depth error. But it's really, really powerful. And it's a lot more similar to stuff like Haskell, to OCaml, than it is to C# and Java. And this lets you model a lot of stuff very elegantly. It's ergonomic in the way, yeah, it's low level, like C, but it's also got a lot of functions and functionality set up so that it's sort of like, it feels like Python. In a lot of it, it's just got clear functions. It's easy to do what you want to do. The community is warm and welcoming. It is one, or probably the most welcoming community that I know. And it's very supportive, and everyone is very welcome. It's challenging, but in a good way. I mentioned the borrow jacker earlier. Once you start working with it, it's kind of hard to get going, because it'll tell you, oh, you can't do this, you can't do that, or hey, you're freed here, but you're using it again here. And at first, that can be a bit of a grind. But once you get used to it, and once you learn why and how it works, it's actually really, really fun, in a kind of a weird, fun way, right? But also, it helps you think about how you structure your programs in general, not just in Rust. And of course, the cute little crab, Ferris, as the mascot. So we've gone over most of this now. So why would Rust be a good tool for video game development? Well, obviously, if it's fast and memory efficient, that's great for a game. That means you can draw more pixels on the screen. It means you can fit more things in a game. That is exactly what you want. It's also not garbage collected, so that means you don't get these sudden slowdowns when it has to sort of collect all the threads and collect all the loose objects. You get away from that completely. And finally, it compiles to WASM really, really well. There's a lot of tools in the web and Rust ecosystem that just put things together. So making that leap from a native binary to a web binary is pretty simple. So WebAssembly then. Okay, cool, we know what Rust is. What is WebAssembly? I was writing this talk, right, and I thought, hey, okay, so this is WebAssembly's logo. It's purple and it says wah. Like, it's purple and it says wah. Now, I don't know if Nintendo had anything to do with this at all, but I also can't say they didn't, so take that for what you will. Anyway, WebAssembly, or WASM, is an assembly-like language for the web. It's been designed to complement and work alongside JavaScript, not necessarily replace it, although a lot of people thought it would in the beginning. That's not really what it's meant to do. It's fast. It runs with near-native performance, as they call it. Basically, it runs faster than JavaScript, and it's great to use for intensive computations. And it runs in pretty much all the modern browsers. So all the big four, like Chrome, Firefox, Safari, and Edge, even before it was Edgeium. So even the old Edge does it. And also, there's something called WASI, or WebAssembly Systems Interface, I think, which allows you to run WebAssembly everywhere, even outside the browser. You'll need a runtime for it, but it makes it really, really exciting, because you can use that to sort of containerize applications, because WebAssembly has a really strict security protocol, so it's great for saying, oh, you don't get access to this and this and that. So, not that I'm the expert here, but it sounds as if it might actually be useful in a similar way that containers are used today. And as I said, it was implemented in 4 major browsers in 2017. That's 4 years ago. It's been around for a while. It's just, you've probably used it, but you just haven't realized. And finally, in 2019, it became a W3C recommendation. That puts it on the same level as JavaScript, HTML, and CSS as language of the web. It is unofficially a big thing. So what's it look like? This is a factorial function in C. You don't need to understand it. It's just, that's what it looks like. Now, in WebAssembly, as I said, WebAssembly is a assembly-like language with a compact binary format. So a .wasm file looks like this. Now, I don't know about you, but this doesn't look like anything to me. It's just a bunch of numbers put up all together. It doesn't really help in any way. But luckily, WebAssembly has another format as well. You've got WebAssembly and you've got WebAssembly text. And the fun thing is, because they got different extensions, so WebAssembly is .wasm. WebAssembly text is what? Yeah. Again, don't know if that's on purpose or a joke or whatnot, but it's actually called .wat. And WebAssembly text is a lot more readable, because it looks like this, which sort of kind of looks like any sort of function you might, or any, if you squint, it sort of looks like a language. But also, you can also make it look like this. If you're into Lisps, this is great, because it's just a bunch of S expressions. Now, these two forms are equivalent, and it's just a different way of writing the same thing. One is easy to read, one is probably easy to edit, depending on how you like editing stuff. The final part then, now that we've got Rust and we've got WebAssembly, is the game engine. What do we do with this one? Here's my choices, the ones I had. Amethyst, Bevy, or write one from scratch. Now, this isn't quite up to date the way it is now. Amethyst is, or was, a game engine in Rust. It has since stopped working on the game engine and started just helping the community and the game engine community itself. Bevy is still active, and a good choice. Write from scratch is an option, but not for me. I would not know even where to start, I mean, this took a while, this thing, but imagine just how much longer it would have taken if I'd have written the whole engine. So, dropped that and decided to go with Bevy, because it was it's gotten so much attention in the ecosystem lately. There are also other choices, I just wasn't really aware of them. Now, and part of the reason I chose Bevy is because I got a good friend who just won't shut up about it. It's great, I love him. And he's got me really into the idea of this engine. Bevy, according to themselves, is a refreshingly simple data-driven game engine built in Rust. It's based on an ECS, or Entity Component System. Again, we're not going to delve into what that means for a game, and I probably couldn't explain it well enough if I tried. But it's different from how, say, Unreal works, I think, or a number of other engines that usually use a scene graph, and instead you've got, you know what, never mind. It's also, as opposed to other engines that I've worked with, there's no graphical editor. Previously, when I've made games, I've used Unity, I've used a bit of Unreal, and they have this nice scene editor, right, where you can place things in and you can move them around and shift them up and down. None of that. Everything is straight from your editor, which is fine, but it's a different workflow, right? You've got to think about things in a very different way. Now, about WASM support. In Bevy 0.5, which is the current version, you need a plugin. But it's very simple. You add a plugin, and it compiles for WASM. Easy. In Bevy 0.6, it will be built in, which is really quite exciting and really just elevates WASM as like a proper target. So, we've got the tools. Time for part two. There's just no way this will work, right? And we'll start by talking about writing the actual game, because that's supposed to be the fun part, right? This is why I did this. I could write a game. Full disclosure, I didn't. The thing is, I had massive plans. And I applied for NDC, right? And then they accepted 2 of my talks and not just 1. And suddenly I had to get a lot of shit done. It's like, oh, fuck, can I do this? Can I do this? And also, when you're writing a game, or just in general, you might know, troubleshooting, that's time consuming. You spend a lot of time just trying to figure out why it doesn't work. So, I originally wanted to look really cool and really slick and present like a maths puzzle game. I took a course in discrete mathematics this spring. I thought, oh, this is awesome. So I wanted to create generate graphs and ask you to find a Euler path around it, or Euler path, sorry, wow. Or you can use modular arithmetic to sort of figure out what's going on there. Didn't happen. So I figured, okay, well, let's simplify it. We'll make a Flappy Bird clone. That's easy, right? It's one thing that bobs up and down, an environment that passes forth. Should be easy. Yeah. That also takes time. It didn't happen. So I ended up using an example from Bevy that they sort of ship with there. And it's Breakout. It's Breakout! Hey! Thank you. Have yourself some extra complimentary coffee on me, whatever. But it looks like this, and it works. So let's see what you need to do to actually make it compile for WebAssembly instead of as a native binary. Because originally, the example targets native platforms. So let's look at the little bits that you need to add to make it run on the web. Parts of it relate to the limitations of the platform. Now, some of these aren't really necessary or relevant for the game, because Breakout is simple enough there isn't any multi-threading going on. But WebAssembly does not support multi-threading as of now. Also, fun thing, Bevy's default renderer is WebGPU, but no browsers support WebGPU as of now. So when compiling for native, you use WebGPU. When you compile for the web, you use a WebGL2 engine instead. It's just a little plug-out you gotta switch out. It's not a big thing. The built-in audio system doesn't work. Again, doesn't really matter for Breakout. There's no sound. But there are plugins you can get that just drop in replacements and work. And finally, if you want to control it using a gamepad, joystick, or a controller, that's not supported on the web, sadly. But now let's look at the bits you need to actually change in your files, both source files and package files. Okay, so the first one. This is part of a cargo.toml file, which in Rust is sort of like a package.json or whatever. It's where you describe the package and all the dependencies, right? In the original Breakout game, this was all there was. I mean, there was a section saying who's the author and what is it, but the only thing in there that wasn't metadata is this. Dependency on Bevy. Now, when we change it to wasm, it kind of expands a little bit. Now, this looks really, really scary, but it's not as bad as it seems. And most of this is actually just saying what I was saying earlier about the GPU, WebGPU, and the WebGL. You'll notice that at the top it says features, and then it says all the default features, and then it splits into native and web. And this is how you tell it how to compile for the various platforms. So here we say, well, okay, use a different renderer when building for native and for the web. For everything else, use the default ones. And finally, because we also added a new crate, or a package, if you will, the WebGL renderer, we need to add that too. Pretty simple. But it's kind of intimidating because it went from 1 line to like 20. Next up, here is a main function. Again, I'm not going to delve into or how this works really, but this is the main function. And this one function has every change I had to make it compile and run on the web. And it's this bit. That's literally all I had to change. It says, okay, when we're compiling for the WebAssembly target architecture, add the WebGL2 plugin. So I said, that's the only change you really had to make. Super easy. Now, this is scary. This is cargo make. This is a makefile-like format. So it's sort of inspired by, I guess, the makefile you use for C, whatever. So it's a build system that's split into tasks. It is actually pretty good, but this isn't something you see in most Rust projects, so it wasn't really something I was familiar with how to use. Now I'm going to run over to this here side, because I can point at the screen. Is that okay? Great. Right. Oh, audio is a bit weird. But yeah, so, and it's great. It runs, and it builds, and it's in the browser. Now enjoy this GIF of Anakin Skywalker a bit longer while I have another sip. So, when you have a game that you're supposed to play in the browser, let's talk about what you need to sort of build and bundle it. Because, I mean, one thing is the binary, right? You can create a binary, but how do you distribute it, and how do you put it on a web page? And also, what sort of things do you need to think about when you build it? Like, what do you optimize for on the web? Is it different from native, or how does it change? Anyway, the first thing we need to do to wire everything together is an HTML file. It's supposed to go on the web. It needs a file, right? And it's really pretty simple. All it takes is this little block of JavaScript which imports and starts the game. Now, this file is sort of included as part of a template for building for the web. And so it's in the repository, and automatically it's built in to like your distribution. And once you do that, it just works. You get a blank page, you get the game. So there's nothing great on the page, it's literally just a blank page. But at least it runs, right? At least it's a game. Now, let's look at the file, because it says it imports init from target wasm.js, right? And this file is over 1,000 lines of magic numbers, of obfuscated lines and names, and it's really sort of nasty. You really don't want to write that yourself. Luckily, you don't have to. It's generated for you by wasm-bindgen. And this is the same crate that we saw the error with earlier, where I had the dependency mismatch. Same crate. Now, this crate is really a lifesaver, because this is what sort of enables Rust to talk to JavaScript in and out and to bind things properly, thus the bindgen. Again, according to them, it's a Rust library and a CLI that facilitates high-level interactions between wasm modules and JavaScript. It's part of the Rust and WebAssembly ecosystem. The thing about this is WebAssembly, by default, really has floats, is it? And U32s, and that's all the types you get. That's a bit hard to work with. If you're used to working with data structures and you're used to working with like anything, I mean anything except for just like numbers, then you want something to not have to think about, oh, what number is this? Luckily, wasm-bindgen lets you use the same types, the same structs, the same objects that you're used to in your coding, so you don't need to worry about it. It's great. It also lets you import stuff from JavaScript into Rust, so you can call JavaScript modules from your Rust code. Super. And you can even like do stuff like manipulate the DOM and all that. It's really, really interesting how they've done it. It's necessary. Another cool thing, if you do TypeScript, it automatically generates bindings. So, all in all, great. Hey, fan. Now, so you use that, and then, when it runs, it's time to make the package small. And this is where the web differs from native, right? Because when you compile natively, you usually want to optimize for speed. You want things to run as fast as possible. You want to render as much as you can. You want to make it run. But on the web, a larger size means it'll take longer to download, which means it'll take longer before users see anything before they can interact with it. So you probably want to change your target and say, actually, I want a small binary. It's okay if it runs a little bit slower, just make it a bit smaller. Obviously, that's a trade-off, and you got to figure out, okay, well, what's right for my game, or what do you want to optimize for? Because maybe sometimes you have your users and you know if they're happy to wait half an hour for your game to download. But usually you probably don't. You probably want them running as soon as possible. But obviously, in the end, you need to optimize for, or you need to measure and optimize what's right for you. Now, measurement is important, because otherwise, how do you know what works and what doesn't? Let's actually look at this, because originally, when I built it, just no optimizations, no anything, just in release mode, it's 12.1 megabytes. That's a pretty large download. That can take a little bit of time, especially on slower networks, right? So it can take a while to get that one down. So let's look at some of the tips we can do, some of the tricks. Number one, and this is where it gets sort of into the weeds. I'll get sort of into how Rust's compilation works and all that, but it's not super important. You can do something called link time optimizations. Now, I'm not a compiler engineer, so a lot of this is above my head. But apparently, it lets LLVM, which is the backend, the low-level virtual machine, it lets it inline and prune functions more often. Which, for you, means you get a smaller binary, and it runs a little bit faster. So this is good. However, the trade-off, you get longer compile times. It takes a bit longer to compile, but you get something out of it. The other thing we can do is to optimize for size. By default, LLVM optimizes for speed. It wants things to run fast, because usually that's what you want. However, we've got two flags to change that. They're called S and Z, or Z, if you will. Now, Z is more aggressive than S. So it should, in theory, give you smaller binaries, right? That's usually the case, at least so I'm told. But sometimes S yields better results. So again, what you've got to do, measure. When compiled with link time optimization to thin, we saved about a meg. That's fine, right? I don't really know what we're looking for in terms of like how much we want to save, but that doesn't seem all that impressive. When we optimize for size, this one's quite fun. Z gave us 12.4 megabytes. The aggressive optimization for size made it larger. I don't know why or what, but that's what it did. Now, using S, it got smaller again, and that's good. So S takes it down to about 11.8, and level Z takes it up to about 12.4. Okay, cool. What if we put them together? Can we do both LTO thin and, like, probably S, right? Or we'll try Z as well and see what's better. Of course we can. When we put them together, the link time optimization and the S optimization takes us to 10.4 megabytes. And the Z just takes us to 10.8. So the S is still performing better. But again, saving 1.5 megabyte out of 12 still doesn't seem very impressive. At that point, is it worth it when you've got to download 10.5 anyway? It's not that much extra to wait, the extra 10%. So, luckily, there's more stuff we can do. Let's look at post-processing. See, there's a tool called wasm-opt, which is a post-processing tool from a package called Binarian, or Binarian. Don't know how you pronounce that. Anyway, Binarian is a compiler and toolchain infrastructure library for WebAssembly and is written in C++. Its aim is to make compiling to WebAssembly easy, fast, and effective. What it does is that it sort of improves on LLVM's optimizations and makes it even better. Again, I'm not a compiler engineer. I don't know exactly how it works. All I know is that it does good stuff for you and it makes your binary better. So, let's see what happens when we try and apply this. Now, we had the S binary, right? There was 10.4. This is both with link time optimizations and with the S optimization. It was the smallest one of the two we had, right? So we apply wasm-opt to it and optimize again for S, and we get down to 6.1. Now this is a lot better. Now we actually we've split the amount of space you need in two. This is great. The other one was a bit larger, remember? But the funny thing is, when you run this with wasm-opt, it gets even smaller. And we go from 12 down to 5.2. Now granted, that's still quite a lot of data to ship. But I'm sure there are websites out there that ship more JavaScript than that, so it's probably not the worst thing in the world. At least we've cut 7 out of 12 megs, which is pretty good, I'd say. Now, if this isn't enough for you, you can also run various kinds of code profiling and other sort of tweaks. There is a code profiler called Twiggy, which is a size profiling tool for WASM. What it does is it analyzes the call graph and it lets you figure out why a function is called. And if we remove that function, how much space would we actually save in the binary? And it also removes sort of the other functions that are affected by this. But we've also got manual interventions. And again, this gets slightly into the weed of how Rust works in compilation, but we'll do it briefly. 1, avoid string formatting. Obviously, this causes allocations because you can't know the size of a string. So the less you can do that, the less space you need in the binary. You want to avoid panics. Panics are what Rust doesn't have exceptions. But a panic is when something happens and just throws its hands up and it's like, I don't know what to do, I don't know what to do, and it just exits. Now, the reason why removing panics work is because to panic, or when you panic, you also get a stack trace. You can use a preprocessor macro that'll stop you from panicking, or when you do panic, you won't get a stack trace, and that means there's less for you to worry about in the binary. You can avoid allocations as much as possible, especially in hot code paths. This is the same for any language that has any sort of allocations. The more you allocate, the more time it takes and the more space it uses. Now, if you can strip all the allocations in your binary, amazing. The Rust allocator takes about, I heard, 10 kilobytes. That means you say 10 kilobytes. We've seen now that we've got 5 megs, 10 kilobytes isn't going to be too much. But like if you're down at that level, it's like, I need to get those final little bits out. Do that. Or use a different allocator. You can switch allocators in Rust to something called walloc. Now, this one's less focused on having predictable performance, but it is a bit smaller. And this one's fun. In Rust, you can use trait objects instead of generics. And without getting too much into it, what this means, when you use a generic in Rust, same as generic in C# or whatever, Rust actually takes this function and monomorphizes it in the output. That means one function gets compiled to however many times it's called, so it's one for each type it's called with. Each one of those, so the function, say you call it with 5 different types, then you get, in the binary, you get 5 different functions. But each use a single type instead. So they're faster, they take more space. Instead, if you use trait objects, you get what's called dynamic dispatch. That means Rust figures out at runtime whether it's this type or that type or that type. It's a bit slower, but you get only the one function, so it takes less space. And that's what we want. And finally, there is a tool called wasm-snip. I think this is a really funny name. And what it does is you can annotate a function and say snip. And then if you know that this function is not called at runtime, it just will be completely excluded from the binary, as well as all the functions that it sort of relies on. Now, I don't know why you would do this or what sort of use cases it's useful for. I've went and checked out the project, seen the README. That's just what it says. And I guess for some reason, if you want it to run, probably if you have what's called a const function, you can run it at compile time in Rust. So you can probably remove those if you know you're not going to use it, which would be useful. Now, all that out of the way, this is an important sort of adage from the bits of optimization. Just like how we let time profiling guide our speed up efforts, we want to let size profiling guide our code size shrinking efforts. Fail to do this, and you risk wasting your own time. And, well, maybe that of your employers, but basically it just means, yeah, you spend a lot of time that you won't get back, and it might not really pay off. So, in summary, remember, kids, that going from Rust to WebAssembly is actually easier than you'd think. The main thing is sort of picking your compilation target when you compile. There are some little amendments that you might need to make to the source code. You might need to make to the build system to make it work. But overall, it's pretty simple. There are a couple limitations to keep in mind, as I said. WebAssembly is single-threaded as of now. And certain libraries and certain workflows might not work depending on what they need, such as controllers or other things that, or the audio, for instance. But finally, with great power comes great responsibility. Now, the power here is for you to distribute a game over the web. But when you do that, remember to keep your audience and your users in mind. So when you build, when you bundle, try and optimize for the right things and measure the outcomes. See what makes things good. And yeah, just make sure that the experience is as good as possible. Now, this is actually all I have. But I reckon, do we want to see the game running? Do you want to see if I can get it up? Yeah, let's see if I can get this. Hey. So we're on this. Oh. Is it going to run? Is it going to run? Seems my browser is a bit sort of not really responsive here because it's not opening the tab. That's interesting. How about we do this? Try and open it again. And shift this to number 1. There we go. So, super simple Breakout clone. And it runs. All right, so that's it. If there's any questions. There's a couple in the back there. I saw you first.
You mentioned that changing the way you allocate might benefit your size of your binary. Have you considered trying another allocation strategy like arena allocation or something?
I have not done this for this specific case, but that is also good, yeah. Like, figure out, obviously, it's like anything, right? I don't have much experience with it, but I'm sort of aware of it. But yeah, like anything you can do to change it or to make it more effective and smaller is probably good. There's one there, yeah?
What is the maximum resolution you can use for games?
Oh, that's interesting. I've never thought to check. Do you reckon? I don't know, or I don't know why that would matter. I think it's the canvas that sort of, this one, wait, so resolution in what sense? Like how large can you make it? Or, don't know. The native one runs up to 4K at least. I'm assuming you can make the canvas larger if you want to. I think this one's 1280 or something. 1280 by what? So 1080? Is that? Anyway, I'm sorry, I don't actually know. But it's a good question. Right, I think, yeah.
What's the performance look like? Human profile?
The performance profiling?
Yeah.
Yeah, we can open that just in the browser here. Do you know how that works?
Well,
Yeah. It's still F12. Boop. There we go. All right, what are we looking for? Performance, eh? Sure. Cool.
you queen.
Yep. Hey! It's a good shout, yeah. So it runs, from what I can tell, usually around, or mostly at 60 and minimum at 26.3, so that's pretty decent. But again, I mean, this is a very simple Breakout clone, obviously. Depending on how complicated it gets, it might or may not work, yeah.
So the large assembly size that you ended up with,
Yeah.
is that mostly due to the size of the Bevy game engine, or is that how it is when you make your Rust wasm things?
That is also a really good question that I don't know. It's Bevy. Thanks. Do you want to sort of elaborate on why it's Bevy?
Bevy is a game engine. You're basically downloading the whole Unity thing inside.
Yeah.
Called, what was it, 6? Call?
Mm.
Yeah. So it is the whole download, because it had to download the whole runtime of Rust and the whole Bevy thing.
All right, so for anyone who didn't hear that, it's the game engine because it has to download and run a whole actual game engine in your browser, and that just takes a lot of space. So the game here is, I think, like 100 lines of code or something. It's pretty simple, so it's not like that massive, but obviously the game engine, to make it run, takes a little bit of a while. Yeah?
The animation, is it smoother on your screen than on the projector? It's a bit choppy.
It's a bit choppy. I don't have it anywhere but on the projector. It depends on how much I've got running on my computer as well, as with everything. But it seems, when I run it on this screen, like locally, it seems perfectly fine. Sometimes it might get a bit choppy, but also that depends on your system. As I mentioned, this is a Linux system, And so it might be that I just configured the GPU way wrong and things just don't work as intended. I don't know. Like, I've used this for a couple of years. I still don't know the first thing about it. I try, and it usually sort of works out. This one in the back.
You mentioned that WebAssembly is meant to sort of supplement JavaScript.
Aye.
So this question is maybe a little wrong, but I'm just curious, are there any efforts to create sort of more general purpose frameworks in WebAssembly so that you can create basically web pages in other languages? Or is that kind of a dead end and WebAssembly is more just for performance-based gaming?
Yes. So to reiterate the question, I mentioned that WebAssembly is meant to complement JavaScript, but is it possible to use WebAssembly to sort of, control the web page so you can build web pages in other languages and not just in JavaScript and not just use WebAssembly for? And the short answer is yes, there is. So I mentioned earlier that you can import JavaScript functions. You can do DOM manipulation in Rust. There are frameworks in Rust, such as the one I'm most familiar with is called U, which lets you build essentially like React or any sort of JavaScript app. It lets you build the whole thing in Rust and runs in the browser. So it is possible. I don't know really what the state of it is. You still need to initialize it from JavaScript and so on and so on. But I don't actually know where they're going with it in the end. But the official stance is always it's meant to complement JavaScript, not replace it. But that might mean that JavaScript does what it does best, which is these little sprinkles, right? And then if you want to build a whole app, maybe that's better done in something else. All right. Anyone else? No? All right, in which case? Yeah.
Question to Rust, like most of the time I try Rust is like the libraries or stuff, SDKs, they are in not stable state, like that's what stopped me from doing it that way. C# or .NET or Python or any language and then stable SDK, and Rust is always on the list, but it's always a little bit not yet stable. That's your experience from using Rust?
Yeah. So the question is, with Rust, it feels like there's a lot of SDKs and libraries that are not stable yet. So what's my experience with it, right? Yeah. And it's true, in Rust, a lot of libraries are still in like 0. Whatever. They haven't quite hit 1.0 any yet. In my experience, that's usually fine. Obviously, I did have this thing that I spent weeks trying to figure out what was happening, right? But usually it's not been an issue. I haven't built any like large-scale apps or anything in Rust, but I've used it for a couple of simple like little web apps or a little server that does this or that, or Advent code and stuff like that. It's usually fine. And I know Rust is used in production a lot of places, and like big places like Amazon and Google and stuff, and they use it. So it does work. And I would probably say look at what libraries you can find, and if you can't find a 1.0, just see what it's all about. Because usually, even before 1.0, they've been quite stable in my experience. Right? Great. Yes.
Is there any way to optimize performance or even limit it to create a more unified experience across different hardware with this kind of setup?
Yeah. So what exactly do you mean by optimizing performance?
Well, mostly limiting it so that you can create the same experience across all the different devices that people will be using. Kind of like when you're making mobile applications, you want a specific experience for everyone, right? You don't want it to like accelerate hardware for other things.
Right. That is very likely possible, but I also do not know. I'm sorry.
No, that's fine. All right.
Yes?
So, you show that like when you compile for WebAssembly,
Yeah.
you get this massive file out.
Yeah.
That has to get loaded. The issue, I guess I'm trying to understand is
Yeah.
with that, how do you debug? Because with like a regular native target, you have all your debugging symbols. With that, all of a sudden you're left with just like this massive file of just text.
Yeah.
So
Right.
are there any tools that like bridges that gap for you?
That's a good question. Now, there's a couple of things I didn't mention, and the question was, how do you debug when you got this massive file that sort of includes everything, right? So how do you debug the compiled binary or the wasm binary thing, right? And what we saw with the compilations and how I compile this, when you compile for wasm, like the compilation takes a while, so it's probably not optimal for when you're developing. You probably wanted to do this for like a release build. And also, because the changes you need to make are so few, when I was developing things and trying to make it work, I would build it for native and just run it on my computer and just debug it that way. And then just hope it works in the browser. I mean, the one thing that we do change here is the WebGL, or the renderer. That might cause problems, but I haven't run into any, so I haven't actually had to solve that problem. But I'd say try and probably run it for native first, and then if you have to run it for the web, there might be ways to do it, but I haven't checked. Did you have a question, right? Yeah.
You partially answered it now, but I was wondering how the developer experience was. Do you have to compile the entire thing?
Yeah.
Every time you make a change?
Yeah, so about that as well. Bevy has a feature called Dynamic, which you can use, which is really useful for development, which lets you, because it'll load pretty much everything dynamically, but just compile the bits you change. And so development-wise, this is great, because that means it takes like a second or two to rebuild. It's pretty much instant, right? You rebuild and you see it. I did not get that working with the build script that I had for wasm, because I didn't really, well, because at that point I just accepted that I'm not going to make a game anyway, I'll just use Breakout, so I didn't really need it. But when working on the actual game, using Dynamic to reload is much, much faster and very smooth. It's also outlined in the docs if you need how to use it. Yep. Do you have one more question?
It was answer the thing about you can do a map file, just like you can
Yeah.
have obfuscated JS to a map file and debug that way in the browser.
All right, so like a source map. Yeah, so you can do source maps to debug things. That's great. All right. Any stragglers? No? All right, then thank you very much for coming along and to listening. It's been really nice seeing you.